We're going to start work today on rotational motion and rotational kinematics. Now, rotational motion is one of those things that, like most of physics, you already have a really good instinctive understanding of. Now, up till now in level 3, we've been talking purely about translational motion. We've been talking about objects that move from one place to another. The stuff we talked about with centre of mass objects, where you push them through their centre of mass and they move from one location to another, where we talked about momentum, where we talked about circular motion, where an object is orbiting around a point, still translational motion. Today we're going to move on to rotational motion, which personally for me, I like to keep the two things clear in my head, as being rotational motion is anything where you're spinning. You've got your internal pivot, often your centre of mass, and the object rotates around that centre of mass. So there's a pivot point and actual spinning or rotation, as opposed to no particular pivot point and merely the object moving from one place to another, translating from one place to another using straight line motion. So the interesting thing about rotational motion is that we're already really familiar with it, and it's often combined with translational motion. So in this unit, we're going to learn the answer to a lot of things that we kind of hand-waved in level 2 physics. Things like why are rifles rifled? Why bother going to all that effort to machine the barrel? And we know, we've learned that objects that spin don't deviate as much from their desired trajectory. And we're going to learn why in rotational motion. We also learn about why the distribution of mass is so important when something's spinning. But first, let's stick with our very, very basic things. And so in translational motion, we talk about distance, we talk about speed or velocity, we talk about acceleration, and we talk about time. And the good news is that all these things still exist in rotational motion. So a lot of this section of our unit is just transferring really basic concepts that we already have into a new format. Instead of distance, if an object is spinning, we have angle, the angle it moves through. So if I draw over here our circling object, and here's its pivot point, this is where it starts, this is where it ends up, this is the angle that it moved through. And I hope you can see that's analogous to distance. If we were sitting on the end of a merry-go-round, for example, we would move through a certain angle. We would have covered a certain distance of the circumference of the object. And I hope you can see that eventually we would wrap round to the beginning and we could keep going, and we could actually end up with covering a distance greater than 1 revolution. So we also have velocity, and you should be able to see that if we're sitting on the edge of our merry-go-round again. If we travel very, very gently, we get to there in a certain time, and we would still call that our speed, how fast we're moving, how rapidly. And fortunately for us, we have a symbol for that, curly W. We still have acceleration. So if we were on our merry-go-round and it was still at the beginning, if it was stationary at the beginning, we would give it a kick or a push or whatever to set it going, and we would go from slow moving, slow omega, rotational velocity, to fast omega. And we call that acceleration alpha, angular acceleration. The good news is time, and we still call that t. Now these things have units, and fortunately for us, and I'll do this in a different colour so you can see, distance is measured in metres, velocity is measured in metres per second, acceleration is measured in metres per second squared, and time is measured in seconds. Now, I hope by now you're going, oh, I bet you there will be a equally delightful analogy between these two things. And the answer is yes. We measure our angle in radians, and I bet you, for those of you who aren't very fond of maths, you wondered why you had to learn about radians, and here's the answer. We don't use degrees, we use radians. it's really important throughout this unit that if you're getting an answer that you're not quite sure how you got, check that your calculator's in radians. Just like velocity is in meters per second, angular velocity is going to be in radians per second, and angular acceleration, radians per second squared, and time still in seconds. So far, so good. We're talking about a really similar type of motion using really similar units and dimensions. Excellent. And we have the same basic formula, just like in level 1 science, we learned that velocity is the change in the distance that you travel divided by the time that it takes you to travel that distance is exactly the same. Angular velocity equals however many radians, whatever angle you've covered, divided by the time. And you can put the deltas on there to show that it's a change in distance and a change in time if you prefer. But I'm going for simple today. Just like with translational, A equals the change in velocity over the time it took to do that change. We've got exactly the same thing going on here. So I hope you're seeing that for today. Sorry, I didn't realise that you couldn't quite see that. But you just roll with it. The T's are still there. They're just not quite on the screen. I hope you can see that this is really, really similar. And Newton's laws still apply for us. So Newton's first law says that a moving object will stay moving or a still object will stay still unless there's an external force. And that's still true with rotational motion. Spinning objects stay spinning unless something acts on them to stop. Exactly the same. So Newton's first law, check, still the same. Newton's second law says that mass and the acceleration you can get out of a given force depends on the mass the object's got. So F equals ma. Force is dependent. If you've got a certain force, you'll get a certain acceleration depending on how heavy the object is, what mass it's got. So if you push something, you'll get a certain acceleration out of it. You'll be pleased to know Newton's second law still applies, but we're not going to talk about it yet because we're going to use some different concepts. But we still have forces. We have rotational forces. We still have acceleration, which we've got up here, and we're still going to have mass, but it's going to be a little bit different this time. And Newton's third law, popularly said as every reaction has an equal and opposite reaction. I'm sure that if we go back to our merry-go-round example, you can understand that if you used your foot to accelerate yourself, to apply a force to yourself on the merry-go-round, well, that force had to come from somewhere. You know, you pushed against the ground and the ground applied a response force back onto you. So that one still holds true as well. So we're going to do a little bit of stuff in class on our basic formulas, understanding rotational motion, but most of our time is going to be spent not on rotational motion in this very basic form, but instead on rotational kinematics. Now, I'm trusting that you're familiar with the idea of kinematics from last year and that I'm not going to need to go over too much. The important thing to remember about all this wall of maths, of course, is that this maths represents velocity, time and distance time graphs, and those are merely visual representations of actual physical phenomena that we can observe and understand. So all we're doing is taking real things that we know about and understand and making them into a mathematical picture. It's a little bit like when we look at a landscape, we can take a photo, we can have a watercolour, but they're still two representations of the same thing. They're two different ways of looking at and understanding the same physical phenomena. Now, you guys might have forgotten, but let's take a look at this one here. VF equals VI plus AT. Now, it may seem at first like there's no real logical reason why we came up with this, but I hope a moment's consideration will convince you that if you know how fast something is moving when it starts, and you know how fast it's accelerating and for how long, let's say an object is at rest, so this VI is 0, it's at rest. It's accelerating at 1 metre per second squared. That is, every second its speed increases by 1 metre per second, and it does so for 5 seconds. I hope that the practical part of your brain can go, oh, well, if I'm increasing 1 metre per second every second for 5 seconds, by the end of it, my speed must increase by 5 metres per second. So if my speed was initially 0, it must now be 5 metres per second. So if you're interested in the derivation of this, we can go through that, but I'm not going to do that now. That's for people who really enjoy understanding how maths relates to real concepts. So over here, we have exactly the same physical representations, but wrapped up in a new cloak, wrapped up in a new way of seeing it. So these ones here dealing with translational situations, these ones here dealing with rotational situations. Exactly the same. The second one here, if we know how fast something was spinning to start with, and we know how much the rate of spinning is increasing and for how long, we can work out how fast it's spinning at the end. So this here we're going to do a lot of practice in class, but this is just using a new conceptual framework, a new language to explain something we're already really familiar with. So I hope this isn't going to be too much of a problem.